Hello everybody. Now today we will be starting the second unit of our curriculum, and that is current electricity. Now this unit has very important and very interesting topics related to the flow of electrons. Till now in the previous unit of electrostatics we talked about the charged particle. But when we were talking about the charged particle, we assumed that the charged particle was at rest. So when it is at rest, there are certain properties of charged particle. But now in this unit, we are going to talk about a moving charge. Now you know some of the background knowledge is there with you about the moving charge. Now charged particle is available in conductors which has very high number of free electrons, and I hope when I talk about or when I spell out free electrons and conductors, you should be able to recall your previous concepts on conductors and free electrons. Now these free electrons are able to move, and when they move in a particular direction forcefully across the conductor or a wire or anything which has large number of free electrons, that constitute electric current. So today we will be talking about the basic concept of electric current and other related quantities. We will also try to understand a little complicated but very important concept of current density and drift velocity. When we know all these, then we will be able to formulate certain equations and formulas which will help you to solve numerical problems. So today's learning objectives are very clear. It will be around this, and now let us start today's journey for another 30-35 minutes and understand starting from the scratch what is the concept of electric current. Now electric current, as you all know, many of you must have experienced electric shock while accidentally touching a plug, or during rainy season it usually happens, or a metallic body of any electrical appliance. So current is flowing, large amount of current is flowing, charged particles are flowing, and accidentally when we touch some of the instruments which are made up of metal, then those charged particles get transferred through our body and we get an electric shock. So we will talk about the concept of electric current, which I think some of you do have a little bit of background, but today we will be more mathematical in our concept, because a lot of mathematics is involved, isn't it, in your curriculum. And it is at times it is difficult. But if we start paying attention to the fundamental concepts very clearly, then I don't think there is any need of any fear regarding these topics. So the current, electric current, is basically defined by looking at a diagram. So let us talk about electric current. Electric current, and later on we will just spell it as current rather than every time talking about electric current. But for the present time we will keep saying it as electric current. Electric current is mathematically defined as the time rate of flow of electric charge across a cross section of any material. And this material, I am writing it in a very general manner, but usually this material is a conductor. But later on you will also study some other materials which are not directly termed as conductors, but they are slightly different. So let us draw a diagram over here and try to understand how mathematically now suppose this is the conductor and there are large number of free electrons in it. Large number of free electrons are there. You know the concept of free electrons. These are electrons which are freely moving in the entire volume of the conductor. Now, if we look at a cross section, a particular cross section, some of the electrons are moving in all possible directions. They are moving in all possible directions. Now, we call it as random motion. We call it random motion. That means almost a similar number of electrons are moving across the cross section. This is the cross section. Similar number of electrons are moving from left to right as from right to left. So the net flow of electron is 0. Right? Do you understand that? Okay. Now, suppose we take a conductor and make this side positive and the other side negative. And therefore, the electrons which are in the conductor, it is something like connecting a battery or a cell across a wire. Now all these electrons will be attracted towards the positive side. So more or less all electrons will be moving towards the right. So if we look through the cross section again, now there is a net flow of electron from left to right. This is what constitutes an electric current. This is what is known as electric current. So electric current, mathematically, we wanted this diagram to be understood first and then write the mathematical statement. Electric current is represented by capital I, and this is equal to small charge which is passing divided by in how much time. So this is called the time rate of flow of charge. Now in differential calculus form, we write I as equal to dq by dt. This is the equation in the differential form, because we have to do a lot of equations and understand the equations in differential form, that is with the help of differential calculus. So this is what? This is small amount of charge, small charge, and this is time interval. How much charge is passing in dt time? dq charge is passing through the cross section. So this ratio is called the electric current. This is known as electric current. Now you can very well judge from this equation, from this basic equation, that the unit, SI unit, if I write SI unit of electric current will be given directly from this equation. Now that will be equivalent to coulomb, because the unit of charge is coulomb, divided by time, that is, sorry, I wrote time, it is, the unit is second. So coulomb per second is the SI unit of electric current, and we call this coulomb per second. This is named as ampere. This is called ampere. Now you see this SI unit of electric current is named after the scientist Ampere, and when we write the name in full, then this first letter has to be written in small case. Remember that. This is the convention. If we write only the first letter, then we can write it as equivalent to capital A. And that is why the SI unit, if written in short just by A, has to be written by capital A. Otherwise, if I write the full name of ampere, then it has to start with a smaller letter A, ampere. So this is the SI unit, and this is about the electric current. Now, there are two types of electric current which are usually talked about, and that is conventional current. What is the conventional current? What is conventional current? Conventional current means the direction of the flow of the current, but it is just opposite to the flow of electrons. So this is the meaning of conventional current. Now it is taken opposite to the flow of electrons. This is just a convention, and that is why it is called conventional current, because conventionally it is found out that since the direction of the electric field is also from positive towards the negative side, and so we always stick to some sort of behavior is there, we always stick to the flow of positive charge. So the direction of the positive charge movement is given as the direction of the electric field intensity. You will remember that. You will recall that. Similarly, the direction of positive charge flow is called the conventional current. But since here electrons are flowing, so if electrons are flowing from left to right, we can assume that positive charge is flowing from right to left, and therefore conventional current is always taken opposite to the flow of electron. And that is what is meant by this equation over here. When we talk about electric current, we usually take it as to be as conventional current and not electron flow. There is another name of or current which is called electronic current. Electronic current. Electronic current is taken to be as flow of electrons. Flow of electrons. So this is electronic current, and usually in today's electrical circuitry, electronic current is not taken as the direction of electric current, but conventional current is taken as the direction of electric current. Now electric current is a scalar quantity. It is nothing but a scalar quantity. So you have to remember that this is a scalar quantity. This is not a vector quantity. This is a scalar because we only know its magnitude and unit to define it fully. That's it. We don't need any direction of electric current. Direction of electric current is along the direction of the wire or the conductor along which current is flowing. So let us take up some other concepts of electric current, and that is how do we define as two types of current. In electric circuits, there are two types of current. Which are the two types? One is called direct current. Direct current is produced by, these are produced by cells or batteries which we use in daily electronic or electrical circuits. The other current is called alternating current. And there are sources, and these sources are called AC sources, which produce alternating current. There are generators also which produce DC current and AC current. So if a generator is producing a DC current, it will be called DC generator, and if it is producing an AC current, then it is called AC generator. Now at this moment I don't think there is any need of the discussion of which current is better, because there is no point of discussion on this. Wherever we require DC current, we use DC, and where we require AC, we produce and generate AC. So it actually depends upon which type of instruments, which type of appliance we are using. But if we try to plot a graph of DC current with time, then there are two certain things which you should observe from this graph. The DC current graph looks like this. With time, the value of the current remains constant. So the graph is flat. It is flat because the value doesn't change with time. If there is a constant current flowing through the circuit, then that is DC current. Even minor fluctuations in the current, because you know that when you use electric current in your houses, at your homes, you will find that at times there is vibration, there is flickering, and that indicates that the current value has changed. So if the value of the current changes, then it is not DC. Then it will fall under the category of AC. So if it is DC, from the cells and the batteries and the DC generator, we get fixed value of current. And this is the graph. I is constant. I is constant. And there is one more thing. No change in the direction of flow of current. There is no change in the direction of the flow of current. If there is a wire and current is flowing from left to right, it will keep on flowing from left to right. There is no change in direction that after a certain time, current will start flowing from right to left. It is not like that. It will always pass from left to right or from right to left, whatever is the case may be in the wire. But in AC, if you see, the graph of the current is like this. With time, the value of the current is like a wave. Is like a wave. That means the value of the current is not constant. It keeps on changing. Apart from it, there is another added feature, and the feature is that the direction of the current also changes. After some time, there is reverse flow of the current from the same wire. So if there is a wire and current is flowing from left to right, then after a certain time period, you will find that in the same wire, the current has reversed. It is now from right to left. So this type of changing, alternating current flows through the wire, and that is why it is named as alternating current. So here we can write comparative points that I is not constant and there is change in the direction of flow of current. Now presently we won't be able to make you understand how this is done. There are generators, there are machines by which alternating current can be produced. We will talk about that maybe in the next few lessons, but presently we have to only understand that there are two types of current. One is called direct current, other one is called alternating current. So these two are the currents that we have to discuss for the time being. So now we are in a position to talk about the next teaching point, and that is electric current density. So let us understand what is meant by current density. Current density is a very unique characteristic property when we talk about the circuit, electrical circuit especially, because at times it is found out that the conductors are not always in a way, their cross sections are not always perpendicular to the flow of the electrons. At times the wires or the conductors are cut, or they have cross section which are slanted, and so there is a difference. There is a difference of what? How many electrons are actually passing through the cross section area if the cross section would have been perpendicular or the cross section is now slanted. So it depends how many electrons are passing through the cross section at a given time. That matters if there is a huge amount of electric current passing through any conductor. So that is what gives us a method to find out how to relate current to the number of electrons passing through the cross section. So let us try to understand current density. It is defined as the current per unit area of cross section. How much current is passing through unit area of the cross section. So if the cross sectional area is slanted, or if the cross section area is more or less, how much current is passing through unit area, and that is the measure of current density. So current density is mathematically defined as, I will write the mathematical formula and then you can see and talk about its unit and other things. Mathematically, current density is indicated by a letter J, very interesting letter. It has no relationship with the current density name as such, but yes, it is now a convention to define current density by J, and this is equal to, in ordinary sense, I over A. And what is I? I is current and A is area. So now you can see that if there is a conductor and we take a cross section which is perpendicular to the flow of electric current, right? And we will take another cross section which is slanted. So what is your opinion? Which area will be more? The black one or the red one? Yes, can you guess? Yes, the red one will have more area. And this has less area, isn't it? Because it is slanted, so the area will be much more than what is perpendicular. Perpendicular areas are the least to the flow of the electrons. But if I take it as slanted, then this entire area will be bigger than this area. Therefore, if I calculate J over here and name it as J1 and J2 over here, I think there is no need of any hint from me. You are intelligent enough to understand that J1 will be greater than J2. Am I right? Why J1 will be greater? Because the area is less over here. And why J2 will be less? Because the area is more over here. So in this way, we can always, in comparison, tell exactly that there are two wires or two cross sections. So where there is more density of current, less density of current, and so on. So this is how there is a different kind of a measure which is done with the help of current density. So this is one very interesting aspect. The second aspect that we are going to talk today is about the drift velocity. Now, drift velocity is another interesting aspect which is often talked about, and we can very well understand what is drift velocity. And apart from drift velocity, I will also let you know some other interesting concepts related to drift velocity. Now see, you have to understand with the help of this diagram. Suppose we have this conductor and there are large number of electrons which are flowing, and if they are flowing in one particular direction, that means they have been either attracted by the positive side and as well as they have been repelled by the negative side. Now, what is your opinion? Do you recall how many electrons are available in a conductor per cc? Yes, I think some of you can recall that it is 10 raised to the power 23. 10 raised to the power 23 electrons are densely populated in 1 centimeter cube of a conductor. It is a huge number. So if all of them are moving together across the length of the conductor, then there are bound to be collisions. Yes, because there is a large number and every electron is trying to move. So there are collisions. Due to collisions, what happens? Due to collision, some of the electrons will stop because they have collided with somebody else. It happens in a very crowded area. You know that at times we collide and then we stop and then again start moving. So similar is the case with the electrons. So if they are stopping for a while and again they are moving because the positive side of the wire is pulling them and the negative side is pushing them, then what happens is they acquire a certain maximum velocity just before the collision, and after the collision they start from zero velocity. So the meaning is that due to, you have to understand this very carefully, and so pay attention here, that due to large movement of electrons, they collide. And if they collide, then what happens? They stop. They stop for a while. And after stopping, they again accelerate. They again accelerate and acquire final velocity. So the meaning is their velocity is continuously changing from 0 to rising to a value and then again coming to 0, rising to a value, again coming to 0, rising to a value, and so on. So we have to find out what is the average velocity of the electron. The average velocity of the electron is known as the drift velocity. And since each electron in the conductor is exactly same, they are all like twins, and large number of twins. Twin means only two, but here there are large number of electrons which are exactly similar. And so each electron will have similar value of the average velocity. So the average, I'm writing it here, the average velocity of the electrons is called drift velocity. It is just a velocity, but it is named as such a drift velocity, and it is denoted by V with a small suffix over here as D. So VD is known as the drift velocity. So this is something which I think you must be able to understand, that what is the meaning of drift velocity. And there is another very interesting concept related to the drift velocity. In the drift velocity, there are two very important aspects which are related, and they are called, one is known as mean free path and the other is called relaxation time. These two are the concepts which you have to understand now. Mean free path is defined as the average path between two successive collisions. Between two successive collisions. So what is the meaning of that? Suppose two electrons collide here, and one starts moving in this way, other starts moving in this way. So they are more or less moving from left to right, but there is a slight change in the path due to this collision. And so when they reach here, one electron reaches here, the other electron reaches here, they again collide with another electron, because there are a large number of electrons everywhere, because all of them are moving. So this path length, one collision happens here, other collision happens here. So the distance between this, the average distance between them, is called mean free path. And this is indicated by lambda. It is indicated by lambda. Now what about the relaxation time? Relaxation time means I will change the color of the ink. The time interval between two successive collisions. So the total time, or rather the average time taken in between two successive collisions. So one collision starts here, over, then another collision starts here, over. So what is the time taken in between two successive collisions? That is called relaxation time, and it is indicated by tau. This letter you have used before in electrostatics to indicate the torque, but now we are using it for relaxation time. Now you can very well judge that velocity is nothing but distance over time. So the drift velocity Vd will be equal to lambda over tau. Very well, very good judgment. Some of you must have judged it before, that the distance is lambda, tau is the time. So average path divided by average time will give us the average velocity, and that velocity is named as drift velocity. So mean free path per unit relaxation time is called the drift velocity. So mean free path, or rather the average, I will write it here as the average mean free path. Mean and average more or less are same thing, so let us not get confused with this. We'll strike it out. Mean free path per unit time or relaxation time is defined as drift velocity. So this is the concept of drift velocity. So I think we have done a lot today. because the entire abstract concept of electric current, its SI unit, how electric current is generated, what happens, and then current density, which is a very important quantity. We will talk a lot about current density later on. And then the drift velocity, the concept of drift velocity, as well as concepts of mean free path and relaxation time, and how are they related. So all these are building to the concept of electric current, and slowly we are moving towards another concept of resistance, and how resistance depends on these quantities that we have discussed. We will talk about that in the next lesson. But before going, I would like you to recall this entire lesson. Try to find out some of the links which are given in the website, and know a little more than what you know right now. Thank you.